Now there are two parts in the proof. There are two parts in the proof of the theorem. The first is, if the equation is exact, then the condition is satisfied. This is the condition. This is the condition is satisfied. Second, if the condition is satisfied, then the equation is exact. Okay, these are the two parts of the theorem. The first part, that is a necessary part, we say. First part. Let us assume that the given differential, differential is in exact form. Let us assume that mdx plus ndy equal to 0 is an exact differential form. We are assuming it. If it is exact, we are using the definition. What is it? Then there exists a function. F, say f, satisfying, what is that? This m must be equal to what? Dou f by dou x, and this n must be equals to dou f by dou. You can see the definition. Satisfying dou f by dou x is equals to m, and dou f by dou y equals to m. Okay. Then we have, what is dou m by dou y equals to? We are going to prove that the condition is satisfied. What is dou m by dou y? Is equals to dou by dou y of, what is m? M is dou f by dou x. M is, so in place of m, we are going to substitute that value here, from here. Dou f by dou x. This is nothing but dou square f by dou y dou x. And what is dou n by dou x? It's to dou by dou x of, what is n here from this? Dou f by dou y, which is equals to dou square f by dou x dou y. But it is known that dou square f by dou x dou y will be equals to dou square f by dou y dou x. Because for a continuous function this is true, and therefore what we get, I name this equation as 1 and 2. This condition we will name it as 1. What is a condition? Yes, this condition we can name it as 1. For the important things only we can give the numbers, and this one we can name it as 2, and this one we can name it as 3. So from 2 and 3, what we get, see, these both right hand sides are equal, therefore dou m by dou y must be equals to dou n by dou y equals to dou m by dou x. Okay, so the first part of the proof is over. What is the second part? suppose dou m by dou y equals to dou n by dou x is satisfied. Suppose the condition is satisfied. So now what we have to prove? Now we want to prove that the given differential equation is exact. M dx plus M dy equal to 0 is an exact differential equation. We have to prove this. So to prove that the differential form is exact, that is, we need to prove that we need to prove, instead of using the word prove, we need to show, we can write anything, we need to show that there exists a function capital F. There exists a function capital F such that, how is that function? This m must be equals to dou f by dou x and my n equals to dou f by, we have to prove that such a function exists. Now let us assume that u equals to integral m dx. We are just assuming a function which is nothing but integration of m with respect to x be the partial integration of m with respect to what? X, keeping y as a constant. So, keeping y as a constant. So that is the value of u. U is nothing but we are going to integrate m with respect to x, keeping the other variable, that is y, as a constant. You can write here y is a constant. Like this you have to integrate it. That is called partial integration. Then, so if u equals to integration of m with respect to x, then if you differentiate u partially with respect to x, you will get m naturally. So now we differentiated this, see, from this we get this step. To differentiate again with respect to x, we get m. Now what we are going to do is differentiating the above equation. Above equation means this equation. Above with respect to y. That's what. So what happens? Dou by dou y of dou u by dou x equals to, right hand side we will get dou m by dou y. That is dou square u by dou y dou x equals to dou m by dou y. So, but what is the assumption we made in the second part? Dou m by dou y is same as what? Dou n by dou x. Therefore, given dou square u by dou y dou x is equals to, is the same as what? Dou square u by dou x dou y, which is equals to dou by dou x of dou u by dou y. So you name this as, see, we will give some numbers. Okay. This one we can name it as question number 4. And this u with respect to x, na? This one will give the number 5, and this can give the number 6, dou n by dou x we can give the number 7, So from 7 and 8 what we get? From 7 and 8 we get, from 7 and 8 we get 1 by dou x is equals to dou by dou x of dou u by dou y. Please see, both the left hand sides are same. See here. So these two must be equal. That is what from 7 and 8 we get like this. This is the 9th equation. Now integrating 9 partially with respect to x. That's what we are going to do. Partially with respect to x. So what happens? We get left hand side, we get n. So right hand side, partially if we integrate with respect to x, so what we get is, we get dou u by dou y. Since we keep integration, while integrating we keep y as a constant, so the constant itself we can put it as some function of y. We don't know what is that. Instead of putting a constant, we will put a function of y, because y is treated as a constant in that integration. This is number 10, where f of y is, where f of y is independent of x. So now from 6 and 10, that is the 6, from 6 and 10, from 6 and 10 we get, so now what is m dx plus n dy? What is m? This is 6 dou e by dou x. Dou e by dou x into dx plus what is n? Just now we found out in previous step, 10 dou e by dou y plus f of y. Dou e by dou y plus f of y into dy. Okay, so dou e by dou x into dx plus dou e by dou y into dy plus f of y into dy. So which is nothing but, so what is this? This is nothing but the total differential of u. You can see the definition I given beginning. So f of y dy. Left hand side is m dx plus m dy. This one again we can write it as du plus, see this part we can write it as, you do the differentiation and then integration. Okay, we do the differentiation as an integration, so we get this term. So what happens is, we can write this one as d of u plus integral f of y dy. So this is an exact differential form. This is an exact differential form, and this completes, and hence this is that function. There exists a function f such that actually this is equal to d of capital F. This is my function. We are able to express the function in the total differential. There exists a function which can be expressed as a total differential form, which is C here. So that is what we have to prove it in part 2. So what is it? We need to show that there exists a function f such that m equals to dou f by dou x and n equals to dou f by dou y. That is nothing but, see, this is my function. See, u plus integral f of by dy. This is my f. So what is df? Dou f by, actually I think this is my f. So what is this? Actually this is df. So what is df? Total differential of f. Dou f by dou x into dx plus dou f by dou y into dy, and it is equal to this one. So you can compare the terms. So what is this? This is nothing but m, and this is nothing but, this is what we have to prove. Okay, and hence the second part. And